See it. Oh, there we go.
Well, we're gonna have to edit this or edit this down, right, to when we start.
Oh, I can't edit videos.
Right.
All right.
My stream.
Hi, everybody. We are Group 3, and this is our Machine Learning and Artificial Intelligence project for decision analysis and system design with Python, IE 4305. So we are going to start with an introduction. I am the captain. My name is John Conlon. Our co-captain is Colby Buddha. Colby, would you like to say hi?
Hello, everyone.
It's our third member, Stephen Childs. Steve, would you like to say hi?
Hello, everyone.
It's our fourth member, Cindy Cruz Rodriguez. Cindy, would you like to say hi?
Hello, world.
It's our fifth member, Aisha, or God, oopsies. Aisha, would you like to say hi?
Hi, everyone.
And we have our sixth member, Khaled Ousmane Axel Kabor. Axel, would you like to say hi?
Hello, guys. Bonjour.
Yes, Axel speaks French. Alan Daniel Rodriguez, would you like to say hi?
Hey there, guys.
And last but not least, we have Leslie Jasmine Salazar. Would you like to say hi, Leslie?
Hello.
And of course, we have our teacher, Dr. Era Leboullec. And to go over what our presentation is going to be about today, we will be presenting to you two different parts. First, we're going to introduce our first introduce our first problem, and talk about our data set about that particular problem. Then we'll go into what kind of question we have developed to make that question work. And then we're going to talk about what research method we are going to use to do that. And then we'll go into great detail about the findings we get from it as well. We'll be doing the same thing for our second data set. Exact same process with the introduction, data set, research question, and our method and our findings. And then we will have a conclusion about how both of them and compare the different methods we'd use and the differences between continuous and classification sets. We'll then go into detail about our references. And now it is time for our introduction.
All right. So, for the introduction, Boston, we have to know that Boston is the capital and most populous city of Massachusetts in the United States and the 24th most populous city in the United States. Boston, we have to know that Boston covers about like 48.4 square mile with a population of 6,075, 647 in 2022, which also makes it the most populous city in New England. We also have to know that Boston also stands out because of the high cost of living in or visiting the city. In fact, it's the second most expensive city in America after San Francisco. I've been there and yeah, it's really expensive. So there, we have to know that there's many different factors regarding the median value of housing in Boston. And we decided to evaluate it through multi linear regression. And yeah, so now we're going to talk about Boston homes price data set. So as you can see, we have tables. We put some pictures on the right side, but we have to know that the data set contains one dependent variable and 13 predictors and 7,084 instances. So for the predictors, we have crime and the crime, which means the crime rate per capita per by town. ZN, which means proportion of residential land zoned for lots over 25,000 square feet. And NDUS literally means proportion of non-retail business acre per town. And chase means it's going to be the dummy variable. Let's say if the house tracks the Charles Rivers, like 1 if yes and 0 if no. NOx is literally going to mean nitric oxide concentration. And we have also RM, which means average number of rooms per dwelling. And as you can see, we have age. The other one, age literally means like the proportion of owner occupier unit built prior to 1940. And we have this, which is going to mean the way distances to 5 Boston employment centers. And we have RD, which is going to mean like the index of accessibility to regional highways. Also, we have tax, which means the full value property tax rate per 10,000. And before the last one, we have like patrio, so PTRATIO, which literally means pupil teacher ratio per town. I mean, by town, my bad, by town. And the last one, which is going to be L state, which means the percentage lower status of the population. So we have to know that for the dependent variable, we have a median value of owner occupied home in 1,000, so the median. And the last one is just going to be the predictive model generate using the MLR. And for now, we're going to talk about the research question, but I will let Cindy Cruz talk about it.
All right. As for our research question, we will be looking into which predictor variable are the most significant in predicting the price of home in the city of Boston. As we have previously discussed in the previous slide, we do have 13 predictors and one dependent variable for a total of 7,084 instances. Now, if you go ahead and look on our next slide, to execute a multivariative linear regression, we use a measure to degree which independent variable and dependent variable are linearly related to each other. The relation is linear due to the correlation between each variable. Now we do take into account those 13 predictors and that one dependent variable. In addition to this, to execute this in Python, we first import the dataset as a .csv file. We then split the entire dataset into a training and test set, with 70% of the data being the testing set and the rest being the training test set. The training set will be used to generate a predictive model. The predictive model is then tested using the data from the testing set. We then evaluate the model and generate performance values to see how well the model fits the data. Now, by doing these, we are able to plot and visualize and compute the performance of our variables. Now, we do utilize model evaluation and prediction and organize our data into training and testing sets and import the data once more time into Python. Now, in our next slide, we will be discussing the findings from the multivariative linear regression model.
All right, so the first thing we took a look at is generating a predictive value, generating a predictive equation using the training data set. And we've generated the coefficients for each of the variables up there, and we also included the residual errors of that data set, of the training data set. Notable coefficients are the fourth variable, which has a coefficient of 4.04, the fifth variable, which is the largest with a negative 13.48, and then the next one of 5.7 for that coefficient. And the model intercept was also generated at 18.92. And to see how well the predictive model fits the training data set. The R-square value was also generated of 0.76. It's relatively high, so it does. So according to the R-square value only, it fits the data quite well. Next slide, please. So after we generated the predictive model with the training set, we then added the testing data. We then tested the training. We then tested the predictive model generated from the training set using the rest of the data, which is the testing set. From that, after testing, we've generated performance values, and the mean absolute error is 3.36. And interestingly, the R-square value changed. It dropped from 0.76 to 0.71, which is as expected because we are adding a lot more data to the original predictive models, and having a lot more data is going to make the model perform not as good as before. So the R-square value did go down. Next, please. Next slide, please.
Oh, sorry.
You good? All right, so after we ran those numbers, we then eliminated any outliers in the full predictive model. And after doing that, the mean squared error increased, which is also pretty expected because we did eliminate a couple of observations, so our error term is going to increase.
That it?
Yep, that's it.
Oh, and I don't think we talked about this, but this is for our continuous data set. Now we will move on to our second data set.
Okay, so for this next data set, it was a non-continuous data set. And so for this, we use a random forest regressor algorithm. So the data set that we found was through Kaggle Online, and which is analyzing the BMI of 500 individuals. So by definition, body mass index is a person's weight in kilograms divided by the square of height in meters. It is an inexpensive and easy screening method for weight categories. So essentially finding if somebody is underweight, healthy weight, overweight, or obese. BMI does not necessarily measure body fat directly, but it can be correlated with direct measures of body fat. So it is very useful in the means that it is strongly correlated with metabolic and diseases outcomes, which are things that are measured by somebody's body fat. So next slide, please. Oh, next slide. Okay, thank you. So this is a BMI data set. In this, we had one dependent variable being the index itself and three independent variables being gender, height, and weight. Gender was classified through male and female, female being 0 and male being 1. Next one is height. Height was measured in centimeters, and the weight was measured in kilograms. And then the next one was the index itself, where 1 is classified as extremely underweight, 3 is normal, and 5 is morbidly obese. And so there was 1 dependent variable, 3 independent variables, and 2,000 instances. Okay, and that was it for mine. Next slide.
All right, so next we're going into our next research question, which was how does weight, height, and gender affect the overall BMI of a person? So to answer our research question, we'll be utilizing the random forest regressor method. It is our classification technique for this project since our BMI data set is non-continuous. So moving on to the next slide, I'll define random forest. So random forest is a machine learning algorithm that is used widely in classification and regression problems using cross-validation. As the name suggests, it builds decision trees based on different samples, also known as nodes and subsets. It takes the majority vote for classification and average in case of regression. While it is creating random trees, it splits into different nodes and subsets. It then searches for the best outcome from the random subsets. Thus, it is like combining a whole bunch of decision trees together into one single model. So you might be asking, why are we using that? Why are we using random forest? Well, one of our main reasons, it provides a higher accuracy through the cross-validation. The random forest classifier will handle the missing values and maintain accuracy. So if there's any missing holes in our data or in the CSV file, if there's more trees, it won't allow for overfitting trees in the model. And then lastly, it has the power to handle a large data set with higher dimensionality. So just to make it like clear up and make a little bit more sense, so we can piece together like the BMI, the height, the weight, and all that other stuff Leslie mentioned before. So I want to give a clear idea about the working of a random tree, and I have an analogy. So for example purposes, suppose we, the algorithm, formed 1,000 random trees to form a random forest to detect a hand from pictures. So each random forest will predict the different outcomes or the class for the same test features. A small subset of the forest will look at the random set of features, for example, the hands or fingers, and suppose some 100 random decision trees predict some unique targets such as a thumb, fingers, or a human. And then the votes of the finger are calculated out of 100 random decisions, along with the votes of the thumb and the human. If the votes of the finger are higher, then the final random forest will return the finger as a predicted target. This type of voting is called majority voting. The same applies to the rest of the fingers of the hand if the algorithm predicts the rest of the fingers to actually be fingers of the hand. Then the high-level decision tree can vote that the image is a hand. So that's kind of how it works. So looking at our slide, some of our important features of random forest is firstly diversity, because not all attributes, variables, or features are considered while making an individual tree. Each tree is different. Immune to the curse of dimensionality. Since each tree does not consider all the features, the feature space is reduced, which is helpful and easier to calculate with. The next, parallelization. Each tree is created independently out of different data and attributes. This means that we can have many different forests on the same single model. The next important feature to keep in mind is the train test split. It's so you don't have to segregate the data for train and test, as there will always be 30% of the data which is not seen by the decision tree. And lastly, stability. Stability arises because the result is based on majority voting and or averaging, which is great. So now I'm going to pass it over to Ellen to discuss our group's results of using random forest regression to see how height, weight, and gender and BMI data set worked out in random forest.
Thank you, Colby. Now, to get a high-level view of what the dataset looks like, we will execute the following command: dataset.head in the Python, which that helps us to get a view of the data, and it shows like a spreadsheet, just like an Excel file. Now, so the final step of solving the machine learning problem, we evaluate the performance of the algorithm. Using the random forest regression, just how explained by Colby, it uses to evaluate the mean absolute error, the mean squared error, and the mean squared error. Sorry. And for a quick explanation, the mean square error is an average summation of the square difference between the actual output value and the predicted output value. And you must have the MSE as low as possible. Now, the lesser the MSE, the mean squared error, the better the regression model is. So, the outputs that we got from the code. The mean absolute error is 1.10046. The mean squared error is 1.964933. And the root squared error, just root squared, which is 1.40176. So this mean squared error is based on the BMI. Thus, this shows in the data the group of people that has been researched shows that they're not majorly obese. Now I will pass it to Aisha so she can finish the presentation.
All right. Thank you, Alan. Hi, everyone. I'm going to be talking about the conclusion in both Boston home prices and BMI data sets, along with the references. Alrighty. So regarding the Boston home prices, we conclude based off of use of MLR or multivariate linear regression method, as it is a continuous data set that showcases different multiple input variables. In our model here, we have significant predictors, CHAS, which is a variable that tells us if the house tracks Charles River, with 0 being if it does not and 1 if it does. NOx, that stands for nitric oxides concentration, and RM, which describes basically the average number of rooms per dwelling. Here in the method used is relatively well fitting our model with R squared of 0.7. Next slide, please. Okay, now with the use of random forest regressor method, our body mass index dataset, we use binary variables with 0 being female and 1 being male. So answering also 1 as extreme underweight, 3 as normal body weight, and 5 as obese. In this case, we use the random forest regressor since the data is not continuous, which is discrete. And the findings from it were not as accurate as anticipated. With, as Alan had mentioned, we want the MSE to be as lower as value is the better. With the mean root square here error 1.4 that showcases that the model does not relatively predict data accurately. Next slide, please. Thank you. So for the references here, basically, it's just all what we got, the resources we used to do our project, basically from calculating the BMI, from our data sets that was retrieved from Kaggle websites, and also how to understand every method and every machine learning method we have used. Also, I want to say on behalf of me and my classmates, I want to thank you so much for watching our presentation, and I will pass it on to John.
Thanks for listening. I hope you enjoyed our presentation and found it helpful to you in learning about things related to data. Have a good day. Stop recording, please.